Hello, everybody. My name is Salvador Pineda, and I'm from the OASIS research group at the University of Malaga in Spain. And I'm going to present joint work with Juan Miguel Morales and Asunción Jiménez Cordero that is titled Data-Driven Screening of Network Constraint for Unit Commitment. So the main idea of this work is whether we can remove some of the constraints from an optimization problem in order to reduce computational time. So to illustrate this idea, I have here a very simple mixed integer linear programming problem where we have x is a continuous variable and y is an integer variable. We have some constraints, and the objective function is maximize x plus y. So this is an illustration of the feasible region. All these blue points are feasible in our optimization problem. And if we are maximizing x plus y, the optimum of this problem is point A. If this is the optimum, we can classify this for different constraints. So for example, constraint 1b here is an active constraint because it's binding up the optimum. Constraint 1c down here is not binding, and then we call this inactive constraint. 1d is a redundant constraint because it's not binding, but if we can safely remove this constraint without changing the feasible region. And then this very particular constraint 1e that we call quasi-active constraint because it's not binding at the optimum. But if we remove this constraint, the optimal point would change from A to B. So this is a very particular type of constraint that shows up in mixed integer programming. So with this example, we can safely remove 1D and 1C, keep 1E and 1B, and just save a problem with a reduced, with a smaller number of constraints. And then we try to do the same with the unit commitment problem. So this is we have some assumptions to keep things simple. We have a single period unit commitment. We assume DC power flow. We have thermal units with a minimum technical minimum. We have renewable units with a capacity factor affected by weather conditions. We have no known demand, and we disregard failures. So this is a very simple formulation where we are minimizing the operating cost plus some penalty for load shedding. This is the power balance equation for each bus, where this epsilon here is the load shedding. This is the bus basically generation equals demands in the system. This is the technical limit for the units, and this is the capacity limit of the transmission constraints, and this is the binary variable declarations. So what we are going to do, these are a very complicated variable because they have to be formulated with full matrices. So in an ideal world, you would like to remove as many constraints to E as possible. So we are going to compare 8 different methods to find out which constraints we can safely remove. So these 5 methods are like kind of naive methods. So for example, well, the benchmark method is just we don't remove any constraint, and then the computational time of the unit commitment is going to be very high. Then we have the single bus approach where we remove all the constraints. It's going to be very fast. It's going to deliver close to optimal solution if the system is not very congested, but in the general case, the solutions are not going to be very good. Then we have the perfect information. This is important because it's going to remove all the constraints that are not binding at the optimum. So, for example, in our example here, this method is going to remove all constraints except 1b, and then it's going to fail to find the optimal solution. It cannot be implemented in practice because you will need the optimal solution. That's what the whole thing is about. Then the naive method is going to remove all line constraints that have not been congested in the past. and it's a little bit conservative. It's going to remove a very small number of constraints. Then we have the constraint generation method. This is going to start solving the unit commitment without any network constraint, like the single bus. Then it's going to compute the flows, and it's going to iteratively add the capacity constraint of those lines that have violated the capacity limit. So it's an iterative method. Then this method is proposed in the literature by Roth and Molson. This problem here is different from the unit commitment in two things. First, it's a relaxation of the unit commitment because it does not include any binary variables. So generators can be dispatched from 0 to maximum capacity. And then the objective function is different because it's going to maximize or minimize the flow through a given line, L tilde. And then the demand is a variable that can change between these limits here. So basically, this problem is going to dispatch all generators, and it's going to choose all demand levels between these bounds. So in order to maximize the flow through a given line. So even if we do so, this objective function is below the capacity limit, then we can safely remove the constraint of that particular line. This method is a bit conservative since it's going to remove all the redundant constraints. Then we have the method proposed in our work. What we're going to do is try to infer line congestions via statistical learning. So we don't need to solve any additional problems as in the previous method. And also, it's not only going to remove redundant, but also inactive constraints. So it's going to be it's not going to be so conservative. We use the k-nearest neighbors approach. So let's say these are two features like, I don't know, like total demand and total wind generation. And then we have a set of points. So the red ones, in the red ones, the line is congested, sorry. And in the blue one is not congested. Then we have a new point, the black one. And then we find the closest, for example, 5 neighbors. In 2 of them, the line is congested. In 3, it's not congested. One may think if this were a democratic research work, you can say that the line is expected not to be congested, but this is a bit dangerous. So we just, in order to assume that the line is not congested, all the neighbors have to be like blue points. And then finally, we also combine this data-driven approach with the constraint generation one. So first we apply the data-driven to infer the lines that are expected not to be congested. And then we check the flows and we add some capacity limit constraints if required. We are going to compare all these methods. Basically, we have the original network and we solve the benchmark model and the exact commitments are determined. And then we run some simulation just fixing the binary variables, and then we get the exact results. Or on the other hand, we can screen the constraint. We solve or reduce the unit commitment problem that's going to be faster than the benchmark. We have some approximated commitment decision that we fix, and then we run the simulation solving an LP, and then we get some approximated results, and then we compare and see what happens. We have tried in a realistic power system in Texas with 2,000 buses and 3,000 lines. We have sampled the electricity demand. So around 10% of the lines become congested at some point during the year. And to test our learning task, we have 300 training days and 60 test days. And these are just the results. On the first column, we have all the 8 methods. This is the percentage of constraints that are removed. This is the variation in the objective function in average for these 60 test days. This is the infeasibilities. This is a percentage of the load shedding with respect to total demand. And this is the cost savings. So there are some interesting things here. So for example, for the single bus approach, it's very fast. So it's only 0.4% of the time that's than the benchmark. But the results are very bad because you have a lot of infeasible and a lot of variation of the objective function. The perfect method, it's also very fast, but you also have some infeasibilities. And this is precisely because we are removing these quasi-active constraints. The naive is removing 92% of the constraints and achieve the optimal solution, but the time reduction are not very high. The constraint generation is also quite modest with respect to time reduction because it has to iterate several times. As I said before, the roll method only removes around half of the constraints, and then the time savings are not very high either. The method we propose is the one that reduces computational time to a lower level, but it implies some inflexibilities and some variation in the objective function, but maybe this is good enough for you. If that's not the case, then you can always combine it with the constraint generation alternative, and then you ensure that you are getting the optimal solution in all cases, and the time reduction are also quite acceptable. Yeah, so this is basically it. This is just a summary. So if you have any questions, I'll be happy to answer them in the Q&A part of the session. Thank you very much.